So this is just for case 3, because you already have case 2. Just don't confuse this part. This is case 3. Now, I'm going to consider the same problem again. So the center is A, this point is B, and the position vector from A to B is still denoted by RBA as a vector. So here, what is the linear velocity at point B if the plane is experiencing both omega 1 and omega 2? So here, for the first one, of course, at the center of A, you still want to consider another linear part. It's a BA, of course, there's still AA. Like this. And we want to find out what is the information at point B. Just like what we did before. We want to know what's the information at point B. And here, for BA, it's going to be AA, and so BA plus this omega is the total of this omega. So this is the omega cross RBA. So in terms of expression, this is actually the same, like in case 2, except that this omega here is this omega here. That equals to the summation of these two. Now, for linear acceleration, the expression gets a little bit messier, but it's still manageable. The first one is AA plus what? Plus the first one is omega 1 dot plus omega 2 dot plus omega 1 cross omega 2. Now this whole thing, as you know, is alpha, right? So this cross RBA, like this. So that's the first term. And plus the next term, plus omega 1 plus omega 2, put them together, and cross omega 1 plus omega 2 together, and they cross RBA. Becomes this. So this is perhaps the most general form in three-dimensional kinematics. And everything we talked about before can be derived from this general form. So you may consider this may be the end of tunnel in three-dimensional kinematics. Because here, if there's no angular motion, there's no angular velocity, you just set this to be 0, 0, and this turns down, right? There's no angular acceleration, and you take this one out, everything's out, and goes back to this one here. So you must memorize this one. Okay, now this is the review on general motion. So I present you how everything is changed and why we have different kind of equations to use. Now let's look at example 31. And we can keep that one over there to see how we use it. To save of time, example 31 is going to be very simple. In example 31, we consider an object. Suppose you can call this like a bar thing like this on the XYZ coordinate system. Now, get the information right. Suppose this bar is aligned at 45 degrees. Forty-five degrees on the YZ plane. This is 45 degrees, and it carries a angular velocity along its longitudinal axis. So this one is called omega 2. And of course, you're provided with this omega 2. The amplitude of this omega 2 is 8 radians per second. And omega 1 is what? Omega 1 is the angular motion or angular velocity of the reference frame. So this is omega 1. And the value of omega 1 is 6 radians per second. You're provided with these two. Now, the objective for this example is to find out the total angular velocity and the total angular acceleration of this bar in this kind of motion. So how do we find it? Well, we will determine this by using this relationship. Remember, in three-dimensional motion, step one is always to convert everything from whatever the scalar form into the vector forms. That means step one is always to write omega 1 and omega 2 in their vector form. So can anyone tell me what is omega 1 in vector form? What's omega 1? Omega 2 is along the longitudinal axis of the bar. Omega 1 is just the spinning of the coordinate system of the of the z-axis. Yes, Alden's correct. Omega 1 is what? It's just 6 times, if you use ijk, this is going to be just k. Is it positive or negative? It's positive, right? Because it's going up. So it's positive. So the positive 6k. And the k arrow means the unit vector. What about omega 2? What is omega 2 in vector form? What about omega 2? Omega 2, to decompose omega 2 to the xyz coordinates. Remember I said omega 2 is on the yz plane. So how do you decompose this at 45 degrees to the y and z? The decomposition is the same as the vector decomposition that we did for linear velocities or linear displacement or linear accelerations. Omega 2, if in this direction it has 8 radians per second, and it will contribute to the y and the z by cosine 45 and sine 45 respectively. So the y component is going to be 8 times cosine 45. Is it positive or negative? It's positive because the direction of y2 is in this direction. So you project it down, it's still positive on y. So it's going to be positive 8 times cosine 45. And the unit vector on the y-axis is j plus another positive 8 times sine 45 degree times k. Correct? Actually, I got it wrong. I mean, this one, omega 1 is 0.6, right? Just correct this one. 0.6. It's not 6. I copied too fast. 0.6. Because that's the number I choose. Of course, this can be any number we want. Therefore, what is omega? Omega is just the summation of these two, omega 1 plus omega 2. And that's going to be, the values I calculated is 5.66 J plus 6.26 K. And the unit is going to be radian per second. So this is omega. And this one is pretty straightforward. It's just like what we said here. Correct? Just like this. Now, step 2. We're going to calculate alpha. And to calculate alpha, you will have to use this expression right here. Now, you know that to find the angular acceleration alpha, you will have to differentiate omega-1 with respect to time and omega-2 with respect to time. And can anyone tell me that what's the value of omega-1 dot here?